Control L.
Right. Right. I gave a talk yesterday, and in that talk I mentioned that at my institute we ran DNS with 0 TTL on some records, and so I'm grateful to be able to have the chance to share some of that information with you today. A starting point for this is a paper from about, well, almost 10 years ago by some chaps at MIT, and they looked at the effectiveness of DNS caching at edge sites. And they did a trace-driven emulation, and when they looked at the DNS data, the first thing they saw that was very noisy. A lot of it was retransmissions or errored packets. But with the trace-driven emulation, they saw that it should be possible to have A records with low TTLs, for example, for below 1,000 seconds, and that such low TTLs would have low impact on DNS load, because that same paper found that examining the DNS traces, there was little spatial or temporal locality in the DNS lookups that they found in those traces. That was a trace-driven emulation, so we decided to actually do the experiment at St Andrews. So we took our entire school network, all the clients and servers, and shoved their A records and various other records down through various TTL values across 4 successive weeks. So we started at 1800 seconds, then we moved to 30 seconds, 15 seconds, and then down to 0 seconds. We also configured all the client systems not to have any caching on the host themselves, and we also configured things like Firefox and IE not to cache as well, so that we would get a full picture of the kind of load that you might get if you had 0 TTL for an entire site. Of course, you wouldn't really do this. My motivation for this was this work I'm doing with ILNP and supporting mobile hosts, which would perhaps be a handful of hosts, or certainly not the whole site. But anyway, doing the whole site was a nice way to get some data. Just some information on how we gather the data and process it. I'm not going to spend too much time on this, other than to say that what I'm going to show you are some graphs to start off with of what happened. And we took a TCP dump of all the DNS packets, and then we bucketed them into 1-second buckets. Okay, so basically you have 1-second buckets, you count the number of queries in the bucket, and therefore you've got a request rate in requests per second. And then I've got a kind of simple spectral analysis on that as well. So here's a basic summary of the stats. We've got 4 data sets, 1800 seconds, 30 seconds, 15 seconds, and 0 seconds. And this column here, the 4th column, shows you all the number of all the packets that were captured during that 7-day period. Oops, what have I done there? And as you can see, this is pretty noisy, because as the TTL goes down, you would expect the number of DNS packets to increase, because it's being the DNS queries are being responses are being cached for less time, but in fact it goes up and then it goes back down again, and that's just to do with the noise that you get in the DNS data. So instead of looking at all of the packets captured, if we select some well-known hosts, so in fact this is our group of all the servers that we run, 67 servers within our school, we get these numbers on the right here, and there you see what you might expect. As the TTL decreases, the number of DNS queries you see hitting our servers increases. But in fact you can see with these numbers, if you compare this final column to the column just before it, regardless of whether you're at DNS at TTL of 1800 or at 0, the total number of good A requests still remains a small fraction of the actual total load on the DNS server. And this was in fact found in the MIT paper, that they found that the good queries were much small, took up a very small proportion of the total number of queries hitting the DNS server. So overall, you can see that going down to 0 TTL, the load increase is significant if you compare it to, say, 1800, because it's doubled, but overall, for the total load hitting the DNS server, it's not a huge increase overall. Here are just some time domain graphs, so of the 1 second bucket. So this is 1800 seconds. The vertical axis is a log scale showing queries per second, and along the bottom here you have time, and that is in Unix days. So January the 1st is day 1. So that's just a 1 week period. We had a little outage here. It's accentuated in this graphic because it's a log scale, but it was actually not a huge proportion of that week. This is what you get at 30 seconds, and again you can see here some of the time of day effects, the peaks during the middle of the day. This is 15 seconds, and this is 0 seconds TTL. And again, if you summarize that as a table and take some basic stats, means, etc., you find that there is an increase, but if we take, say, 1800 seconds as a baseline, here we had a mean request rate of 3 1/3 requests per second. If we compare that with 30 seconds, which is a 60 times drop in the TTL value, you see only about a third increase in the mean DNS request rate. And if you compare 1800 seconds to 0 seconds, again, it can be seen as a significant increase compared to 1800 seconds, that it's more than doubled. But overall, it's for the total load hitting the DNS server, it's not a huge amount of traffic, and the peak rates you get are still pretty low compared to what's possible with modern hardware. So the load has increased, but not as much as you might think. Okay, so here's a quick spectra analysis as well. Here, what we want to do is look at the distribution of the request rate. So what I do is I take the 1 second buckets and I count the number of times a bucket of a particular value occurs, and I plot that. And so I get a kind of poor man's periodogram. So this is the plot we have for 1800 seconds. Again, how to read this graph as follows. It's a log-log scale. On the left, we have normalized request rate. So it's a request rate normalized over the whole week. And along the bottom, we have the query rate again on a log scale. So for example, how you would read this point just here is that saying that 20% of the requests for that week were at 1 request per second or less. So 20% of the requests coming in, request rate coming in. How you would read this point here, that's saying that 1% of the requests were at 10 requests per second or less. This graphic in the bottom right-hand corner is a cumulative distribution of this thing in the top left-hand corner. And again, a good point to take here is, on the bottom axis here, is the value 10. What that's saying is that about 90% of the queries you were getting in for 1800 second TTL were 10 queries per second or less. Okay. And if we look at the other TTL values, so starting at the top row, that is 30 seconds, 15 seconds, 0 seconds. If you look at those graphs, you can see some differences as you move down from 30 seconds, 15 seconds to 0 seconds. But it's not a huge difference in terms of profile of requests. If you look at the cumulative distributions in the right-hand graph, you can see this 10 is a good point. That's still about 90% of the packets coming in are coming in blocked up as 10 queries per second or lower. Okay. So what is possible if you have DNS TTL set to 0? Well, as I said, my motivation was to use it to support mobility for this thing I'm working on called ILNP. In fact, there has been previous work looking at using DNS mobility unrelated to ILNP, but then we've got some other slightly crazy ideas we want to try out with ILNP if we can get low TTL values to be usable. I'm not going to go through those in detail. But who would actually use low DNS TTL values today? Who's crazy enough to do that? Well, we have some crazy Yahoo people who are using about 60 seconds. Akamai uses a 20-second TTL. And then at the moment, again, just in case you don't believe the numbers, I got our chaps last night to run the whole site again, just for you, for 0 seconds today. There are some things you wouldn't do. This would only be for edge sites. You wouldn't set 0 TTLs for records higher up in the server hierarchy. You would also not do things like use low TTL values for your NS records, and for services like email, etc. MX records you need to keep at a higher TTL. In fact, we did try them with a low TTL. I have some stories about that, but that will have to wait for another talk. So summary, 0 TTL for DNS on edge sites doesn't seem to be introduce as much load as you might think, and seems usable. And therefore frequent access to DNS servers when you have low TTL seems practical. What we want to do is see what happens now when you have secure dynamic DNS update and you have authenticated DNS records. What's the additional load on a server when it has to deal with the crypto overhead associated with secure DNS? I'd like to say a very, very big thank you to our sysadmin group, who I managed to persuade to change the operational settings. The settings are on our operational DNS server down to 0 TTL. Thank you for your attention. If you, I may or may not have time for questions, but if you want to prove for yourself that we're running at 0, just take any one of those names, add CS St Andrews AC UK, run dig, and you should find you get 0 back. Thank you.
Thank you. Are there any questions? No. Oh, there is.
So I was Robert Evans from ISC. I was initially kind of skeptical of your results until I saw that you were studying child nodes rather than the NS delegations and name server addresses. This is not really a question, but I did want to emphasize the fact that the DNS would absolutely collapse if if the infrastructure records were not cached across the global system.
Yeah, agreed.
So I have a question on methodology. So I've been looking at a lot of different things where people do things that look like science.
Right.
And, that can be really dangerous. And in this case, what I want to ask you is, how are you avoiding finding what you're looking for? In other words, you have a certain kind of confirmation bias in this whole thing, right? Because you want it, like the list people have this too, right? Or they're trying to build a system and they want to find data that confirms what they want it to be, right?
Right.
And so the good science puts controls on that, right?
Right.
So do you have anything that's controlling that?
So you're saying...
So there's this thing called confirmation bias. In other words,
right.
when you want to find something and you look real hard, a lot of times you can find it.
So you're saying, do we have something to show that the load is unacceptable?
No, it's more like a control on your process, right? I mean, there's no control, you don't do a real experiment because there's no control, right?
Yeah, so we thought about this, and what we were concerned about was what would happen on a real operational system. So it's very hard, I think, to run a control experiment on a real operational system. What we would want to do, perhaps, is get lots of users using the labs doing a very particular thing, and then we would be able to generate a control data set. Okay. Now, that's just impractical. Your point is well made, but I think it's a difficult thing to do. So we thought the next best thing we could do was just change the operational settings, assume that on a week-by-week basis that the usage of the system is similar, okay, and based on that, we can see that if we change the TTL, that's the only parameter we're changing, and so we can make comparisons across the week. Now, in fact, you will have seen from the time domain data that, in fact, it's not true. We have this little outage here at 1800 seconds. There's a little peak just here. That was, in fact, a class test I ran, and so they were hammering the servers a little bit. So it's very difficult to put the control in. I've been told I'm on time, so thank you very much.
Thank you so much, Saleem. Okay.